Okay, today you're going to learn about free body diagrams. Free body diagrams put everything we've been teaching into play. Alright, so free body diagrams. A free body diagram shows all of the forces acting on an object. F subscript G. So F of G is the force of gravity or the weight of an object. Force of gravity or weight of the object. Synonymous. Mean the same thing. The symbol can be F of G, F of W, or just plain old W. The formula is usually seen as W equals mg. That's kind of going away as people are trying to emphasize the fact that it is a force. We're going to use F subscript G. We're going to use G being 9.8 meters per second squared. It'll be positive because we're always going to compute the weight of an object as being positive. F capital N, F subscript N, F of N is the normal force and is the force that a surface applies to an object due to contact. So if you have an object on a desk, gravity pulls it down, and since the object isn't pulled through the paper, through the desk, that means the desk has to push up with a force that is equal. So in this instance, the normal force is equal to the force of gravity, or the weight of the object. And we're going to be only doing things that are on the horizontal or on the vertical. So if you're a person, and you decide to lean against a wall, that's an awfully long arm, huh? Whatever force you apply to the wall, let's say it's 10 newtons to the wall has to push back with a force equal to that at 90 degrees, also at 10 newtons. Because Newton's third law says for every action there has to be an equal and opposite reaction. So the normal force is equal to the force that the object applies to the surface and occurs at a 90-degree angle to the surface. F of F is the force of friction and always opposes and always in the opposite direction of the not net force but motion. Friction always opposes motion. T is the tension force on a wire, cable, rope, anything like that that's allowed to use to hang something, and it can be shown as force with a T at the bottom for tension. F net is the net force and is equal to the sum of all forces. And if we rearrange the formula to solve for acceleration, we rearrange F equals ma to A equals. I'm going to put F net in here, because it's the net force that will give us our acceleration. So A is the F net over M. Okay, so then it's just practicing free body diagrams. So what's going to happen is we're going to draw a diagram on the left side of our paper, and on the right-hand side we're going to do our math. So as we do this, make sure that you are practicing that so that you don't run out of room. All right, we're going to always approach this the exact same way. We're going to find the mass of the object, figure out the forces that are being applied, and then solve for what they want us to solve for. And what I've done is I've put every one of these in a situation where you solve going left to right. So as you come to something, solve for it, they lead into each other. So a 3-kilogram object is being pushed east with a force of 30 newtons. It's being resisted by a force of 20 newtons to the west. So what we're going to do on the right-hand side is write our mass, 3 kilograms. And then we're going to put that on a surface. That can be the ground. Since we're pushing it east, east is to the right at 30 newtons, and to the west at 20 newtons. Because we're pushing it left and right, it has to be sitting on something. So the ground or a table, it doesn't really matter. All right, from there, we've got our drawing of what's going on. Now we're going to find FG. FG is directed from the object downward. So FG equals mg, where m stands for mass and g stands for the acceleration due to gravity, which is 9.8. So 3 times 9.8 gives us 29.4 newtons. So to help yourself out here, you can pause the video whenever we put stuff up and see if you can work it, and then you'll see what our solution is. Now the normal force occurs down here at the contact point. It's where the table pushes up And so it's going to be the normal force for us is going to be equal to the force of gravity. And so that's 29.4 newtons, because that's how much force the object is putting on the table. Now, generally what I'm going to do as we progress on this is, because these arrows in the past, my students have had a hard time with these arrows going the opposite directions. And we've seen this, I've seen this drawn many different ways in many different books. It doesn't seem to be that you have to put the force vector at its origin point. I've seen them put it down below. And we're just going to show it being above so that it's easy to draw. We're going to have the arrow going up, force of Newton, and you'll see as we progress. So we just did Fg and Fn. Fnet is found, now on the y-axis, the normal force going up and the gravity going down. They will always counteract anything if you're on a surface. So we're not going to worry about the y-axis when we're on a surface, because they'll counteract and come to a net force of 0. On the x-axis, we have 30 newtons going right, and we have 20 newtons going left. When things go in opposite directions, you're going to subtract the numbers, and you're going to put the larger number in and subtract the smaller number, and the arrow with the larger number will choose that direction. 30 is larger than 20, so we'll do 30 minus 20 and get 10. The arrow for the 30 is to the right, so he's the winner. And then our unit is newtons. That's the way I'm teaching my students, so we don't have to worry too much about positives and negatives because they get confused. My acceleration is going to be found by finding the Fnet divided by the mass. So my Fnet I just found, it's 10. And then my mass is 3. So your acceleration is going to be 3.33 meters per second squared. To the right. So it looks like it takes a lot of work, but it's really very limited, very simple steps. So let's do those steps one more time. We have a 12 kilogram box pushed to the left with a force of 25 newtons. It's resisted by a friction force of 2 newtons. Okay, so again, 12 kilograms, putting my mass inside a box. Now if you're an artist, you can draw objects. I am not an artist, so I do not draw objects. I put everything in a square, in a box, and then I do my math from there. The left force of 25. The right force of 2. How did I know that my resistance must be to the right? Friction has to be to the right. Friction forces always resist motion, and since the only force being applied is to the left, friction has to oppose the motion, so it's got to be in the opposite direction of the movement. I'm going to find gravity first. That's going to be down. Force of gravity equals mg, where it's 12 times 9.8. Put that in your calculator. Pause the video if you need to. It's going to be 118 newtons. So we did Fg. Normal, the normal force is going to be directed upward from our tabletop or ground, and normal force is going to be equal to the force of gravity, and that's going to be 118 newtons. The net force, so I did force of normal, is going to equal the 2 newtons to the right plus the 25 newtons to the left to give us 23 newtons. Opposites here, so subtract, and the winner is going to be to the left. Our acceleration is going to be Fnet over mass. That's 23 over 12, and that will give us 1.92 meters per second squared left. So for this one, I'm going to go ahead and write left just so you can see that you can put left there instead of an arrow. You can even write the word west. We will accept west as left, or an arrow left, or the word left. All right, 2 men with a combined mass of 207 kilograms are in an elevator rising at a constant speed. Okay. So rising at a constant speed. Rising at a constant speed rising at a constant speed.
You still here?
So the two men with combined mass of 207 kilograms.
How do you make the iPad?
You just draw it. Or in an elevator that is rising at a constant speed. Now, if you're moving at a constant speed in a constant direction, up in this instance, that means that your acceleration equals 0, and that's going to be important for us later on. So we have our combined mass, we have an elevator, we have a cable, so that's a cable. I have my students write cable out beside it because I think when they look back at their notes later on, they'll be thinking, what is that thing that's right there? Put two people in here. Gravity's going to pull those two people down. Now what I really should have done on this problem was put the mass of the people and the elevator. For our purposes today, let's just act like the elevator has no mass. I know that's dumb, but it's going to be what we're going to have to do because I wrote it this way and made a mistake. All right, so if we find the weight of the two people, it's 2,029 newtons. Now the normal force will be the force that the floor pushes up against these two people, supporting their weight. That's going to equal the weight of the people, which is 2,029 newtons. Now in the cable, we're going to have a tension force up, also of 2,029. Here's where it gets a little bit bizarre. The weight of the people has to be supported by the floor, so it has to equal their weight. The cable will attach right here to the elevator, and so we're going to have a downward force right there of the weight of the elevator plus the people. So this is where I should have had something different going on, but I didn't. So the only way for the students to solve this is to act like the elevator has no mass, and we're only solving for the mass of the people. So that's my FG, my FN, and my T. F net will be 0 because F net is mass times acceleration, and my acceleration is 0. Cool. All right, so let's do one where we don't have a contact force. So let's have a rocket that's being propelled upward with an acceleration of 3.7. Okay, so same thing. I'm just going to draw my square over here. I told you I'm not an artist. Now this object isn't going to be in contact with anything. So F net, F normal force, there's no normal force because we're not in contact. So we have a force of gravity directed downward. And that's m times g, which will equal 200 times 9.8. And that is going to be 1,960 newtons. Our object is going upward with an acceleration of 3.7. So my net force is mass times acceleration. So that's the 200 kilograms for the rocket times its acceleration up of 3.7. And that gives us 740 newtons up. Now from this information, I did not ask the students to solve for the thrust force of the rockets, but I could have, and we would have done it by saying if the rocket is being pulled down by 1,960 newtons, but it's going upward with a net force of 740, to find the thrust provided by the rockets, force by the rockets, that would be the 1960 for the weight plus the 740 for the acceleration we're actually seeing, the net force we're seeing applied to it. That would mean we'd have to have 2,700 2,700 newtons of force going up, provided by the rockets. So using common sense, we can solve for that. All right, we're going to save problem number 5 as a review before kids do the problems for grade. So I'll just save that for later on. Good luck out there.